Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome back. This is lecture 4 of week 2, and we're going to be talking in lecture 4, we're going to be taking a quick look at some of the novel materials and structures that people are looking at these days to try to improve the performance of thermoelectric devices. So I want to remind you in every lecture what the transport coefficients are, because we need a good, clear understanding of these equations, the electrical part, the thermal part, and the lattice thermal part due to electrons and the thermal part due to phonons. And we need to keep reminding ourselves of the way that we write these coefficients. The simplest way to write them is conductivity is quantum of conductance times number of channels in the Fermi window times average mean free path. Seebeck coefficient simply related to the average energy at which current flows with respect to the Fermi energy. The Peltier coefficient is fundamentally related to the Seebeck coefficient. The electronic thermal conductivity is related to the electrical conductivity through the Lorentz number. And the lattice thermal conductivity we'll talk about in lecture 5 looks very much like the electrical conductivity. So these are our fundamental equations. And when we address these equations, when we address these topics, we want to be thinking about what changes when we do, for example, real band structures. How do we decide which band structure would give us the best performance for a thermoelectric device? What happens when we reduce the dimensionality? That's kind of a theme in materials research these days, nanowires and quantum wells and things like that. When devices get very short, we can have ballistic transport. So we want to talk a little bit about what changes when we do ballistic transport. And one example of ballistic or near ballistic transport is a thermionic device, which is another kind of power generation or cooling device that's a little different but very similar to a thermoelectric device. Okay, so let's jump in. So we've been thinking so far in terms of very simple band structures. We have very simple relations if we look at the energy versus K plot or H bar K crystal momentum. We've been taking very simple descriptions of energy versus momentum for electrons or holes in terms of an electron effective mass or a hole effective mass. And if the band structure is simple, then very near the bottom of the conduction band or top of the valence band, this is not too bad. Okay. And we've seen that under these conditions, we can simply derive the number of channels in the band. And for a 3D material with parabolic bands, the number of channels at an energy E is proportional to the effective mass of the conduction band, and then increases linearly with energy as we go into the band. For the valence band, it's proportional to the effective mass of holes in the valence band, and then it increases linearly as we proceed into the valence band. So this is the simplest possible example of a band structure and what happens for a very simple band structure. But real materials may have very complicated band structures. So for example, this is a computed band structure done by a DFT calculation by Dr. Jesse Mason, who you'll be hearing about in the final lecture this week. And the band structure looks very, very complicated. But as you'll learn in the last lecture this week, which is really a bonus lecture for those of you that would like to go a little further and learn how we treat complex materials, there is really a very simple numerical procedure that we can use to extract from this complicated band structure the number of channels versus energy. So here's the band gap, centered about 0, and the number of channels increases in the conduction band and increases in the valence band, but it's more complicated than the simple parabolic band case. Nevertheless, you will notice that if we stay close to the bottom of the conduction band or top of the valence band, we could, at least to first order, approximate the number of channels by a straight line, just the way we do it for a parabolic band semiconductor. However, there's no need to do that, because once we know M of E, we can put that in our formulas for the thermoelectric transport coefficients and just do the integrals numerically, and we have the result. So as I mentioned, Dr. Jesse Mason will be giving us a lecture, the final lecture this week, discussing in more detail how you do these calculations and how you can make use of an online tool to do them if you have an interest in doing so. Okay, so what we're going to be discussing here, first of all, is how do we maximize this figure of merit? If we could choose any material, or if we could engineer the properties of the material, how do we maximize the figure of merit? Well, the very first thing we would do is to select a material with a low lattice thermal conductivity. That's something that we're going to be discussing in the next lecture. We might also look at reducing the electronic thermal conductivity, although that doesn't play a big role in most semiconductor thermal transport. We could also maximize the numerator. We could look at what could we do to select a material that will give us the biggest possible product of S squared and sigma. Okay. So one of the questions that people have been asking, and you would think that there's an answer to this, but so far there isn't a clear, simple, convincing answer. And that is, if you could choose any band structure to maximize the electronic performance, the numerator, what would that band structure be? Well, we can sort of understand the general considerations of what we would be looking for. We have some kind of conduction band where if it's parabolic, the number of channels just increases linearly with energy. It might increase in a more complicated way. We position the Fermi level somewhere close to the bottom of the band. We position it in a way that the Fermi window, which has this width of a few kT about the Fermi energy, overlaps with the channels in the conduction band. If we can keep the Fermi energy low, then we get a high Seebeck coefficient. But if we can overlap with a significant number of channels, then we get a high electrical conductivity. And that's what we try to do. We try to do both. So we have to keep the Fermi level as low as we possibly can, away from the band edge. But we also have to maximize the number of channels. So if we had a very high effective mass, we would have the slope of this line would increase more steeply, and we'd get more channels inside the Fermi window. That would give us a higher conductivity. We also want a long mean free path. Mean free path is velocity times scattering time. To get a high velocity, we want light effective masses. Okay. But light effective masses give us a small number of channels, so there's a trade-off involved there. We also want to minimize the amount of scattering. Mean free path is velocity times average time between scattering events. To minimize the number of scattering, we want to minimize the number of states that we scatter to. That also requires a small effective mass, just the opposite of what it requires to maximize the number of channels. So there are some very severe constraints here. And you can think about more complicated band structures and anisotropic band structures that might help you make these trade-offs. But it's not trivial to try to select the band structure that would give you the optimum thermoelectric performance. So the question is, if we could choose anything, is it clear what we would choose? Well, let's look at something very simple. Let's say that we could put all of the channels at the bottom of the conduction band at one energy. What would that do for us? Okay, so if we take a look at that, if we look at these expressions, it's interesting. You can just plug a delta function into the expressions we developed earlier, and what you will find is something very interesting. The electronic thermal conductivity goes to 0. Okay, so a delta function makes the electronic thermal conductivity 0. Well, that's very nice. Okay. Now, how do we think about that physically? There's a simple way to understand that, and Professor Dada discussed that in week 1. We're talking about the electronic thermal conductivity measured under open circuit conditions. So what we do is to open circuit the electrical current flow. We measure the heat flow. We divide by the temperature gradient. That's how we define this open circuit electronic thermal conductivity. But if there's only one channel that electrons can flow in, and if we've open-circuited that channel so that the electrons can't flow and give us an electrical current, they also can't flow and give us a heat current. So by that simple physical argument, we can see why the electronic thermal conductivity is 0 when we put all of our channels at the same energy. Well, we might wonder if that's the optimum band structure. So a way to do that is to look at these arguments made by Mahan and Sofo in a very important paper published a number of years ago. Here's our thermoelectric figure of merit. Remember the connection between the electronic thermal conductivity under open circuit conditions and under short circuit conditions. You can see it's related to the product S squared sigma T, which is the numerator of our figure of merit. So we can put these two equations together and we can rewrite that equation in an equivalent way. It's the ratio of the electronic thermal conductivity measured under short circuit conditions to the lattice thermal conductivity times this factor, which if you take a look at it, you can convince yourself is always less than or equal to 1. Okay. Now, if we look at that factor and we say, aha, we'll make it as big as we possibly can, we'll use a delta function, we'll find a material that has a very sharp distribution of channels, almost a delta function, and we'll make that term, that second term, close to 1 as possible. Now, if we do that, what we're going to find out is that Zt is always then less than or equal to the ratio of these two thermal conductivities. And what we're going to find out, though, is that if you use a delta function, what you will observe is that it does make the second factor 1, which is good, but it hurts the first factor even more. So a delta function is not the best choice, and it's still an open question, I think, as to what exactly the best choice still is. So in terms of this best band structure question, this is a question that has proven to be hard to answer, but we're going to need to come to grips with it and if we're going to continue to improve thermoelectric device performance. The basic general goals are clear. We want to increase the number of channels near the bottom of the band because that increases the electrical conductivity, but we have to, at the same time, we have to make sure that those increased number of channels don't give the electrons more places to scatter to and reduce the mean free path so much that we don't get an advantage. That's a fundamental trade-off. So we can accomplish this. We can put more channels together by exploiting valley degeneracy. We can have many different valleys in different parts of the Brillouin zone, giving us lots of channels. We can strain materials or produce alloys that will produce different valleys together. And if we do that carefully and we can increase the number of channels and not hurt the mean free path too much, we can get a bit of an improvement. Now, another way that we can engineer the distribution of channels in energy space is by reducing dimensionality. So I would think of reducing dimensionality as just another way of engineering M of E. So this has received a lot of attention recently, so let's talk about it just a little bit. We've been talking about a large bulk thermoelectric with a large cross-sectional area A. Let's talk about a nanowire thermoelectric. A very small wire, very small diameter with the same length L, and ask ourselves, what are the thermoelectric properties of that nanowire? Well, this wire, if it is small enough in diameter, the properties are going to be altered by quantum confinement. The way we would get a handle on that is we would look at the de Broglie wavelength of an average electron. It's just Planck's constant divided by the momentum of an average electron. If I take average p squared over 2m, that should be my average kinetic energy at equilibrium. That should be 3/2 kT. So that gives me a way to estimate the thermal average de Broglie wavelength of an electron in this material. And if you put numbers in for a material that has an effective mass of equal to the electron rest mass, you'll find that the de Broglie wavelength is several nanometers. If you put in a light effective mass material, it'll be the de Broglie wavelength then will be even bigger, and the quantum confinement will occur at even larger dimensions. So when the size of the structure approaches the de Broglie wavelength of the electrons become quantum confined and their properties are altered. The biggest change for us is that the density of states, which goes as the square root of energy in 3D, goes as 1 over the square root of energy in 1D if we have a parabolic band. So that's quite a dramatic change. So if we look at the density of states in 1D, 2D, and 3D, we will see that the density of states versus energy goes as the square root of energy in 3D, independent of energy in 2D, and 1 over the square root of energy in 1D. So they're dramatically different densities of states. But what we need to look at is the distribution of modes in energy, because that's what the important quantity for the thermoelectric transport coefficients. That's proportional to velocity times the density of states. And when we do that, we find that the distribution of modes in energy is constant above the band edge in a nanowire, goes as the square root of energy in a two-dimensional quantum confined sheet, and goes linearly with energy as we've seen in a bulk thermoelectric. Okay, so bulk thermoelectrics are okay. We have a few channels at the bottom of the conduction band, not as many as we would like. 2D is a little bit better because the number of channels increases more rapidly near the bottom of the conduction band, so that Fermi window will encompass more channels and give us better performance. And nanowires are even better because we abruptly step up to the number of channels and we get the best possible structure that we could hope for. Now, if you do some calculations, you might notice, for example, that if we look at the Seebeck coefficient versus location of the Fermi energy, 0 is when the Fermi energy is right at the bottom of the band. You can see if we're well below the band, we get a high Seebeck coefficient. If we're well above the bottom of the band, it begins to approach 0 like a metal. If I look at 1D, 2D, 3D, you see that the Seebeck coefficient for a given Fermi energy is biggest in 3D and smallest in 1D. The simple physical explanation for that is that the channels are more spread out in 3D, so that the current flows at an average energy that is higher than the Fermi energy. In the 1D structure, we get most of the channels that are in the Fermi window are located closer to the bottom of the conduction band. They're less spread out, the energy difference is smaller, and we get a smaller Seebeck coefficient. But it's interesting to look at these black arrows here. They show you the Seebeck coefficient when you've optimized the figure of merit. When you optimize the figure of merit, you don't need to put the Fermi energy as close to the bottom of the band in 1D as you do in 3D, because there's a bigger increase in channels at the bottom of the band in 1D, so we can keep the Fermi level lower. So you see the optimum location of the Fermi energy is lowest in 1D, higher in 2D, and then even higher in 3D. So what that means is that at the optimum power factor, we get these different optimum locations of the Fermi energy, and what that translates into is the fact that S squared will be 40% bigger at the optimum location in 1D than in 3D. So that's a very good reason to think about 1D thermoelectrics, because we could optimize the performance of S squared. Now, the only difficulty with that is that in order to make this work, we need isolated nanowires that are quantum confined. And now when you start thinking about packing fraction issues, how closely can you space these? In order to pump any significant amount of heat, we need as many channels as possible, which means we need as many nanowires as possible, packed as closely as possible. And once you start thinking about these packing fraction losses, it becomes difficult to get any really large advantages from nanowires. One of the things the nanowires do, though, is that their roughness increases phonon scattering a lot and significantly reduces the lattice thermal conductivity, and that's very beneficial. So, reducing dimensionality is just a way to engineer the number of channels versus energy. There are other ways to do that: alloys, strain, different materials. The electronic performance should be improved a little bit. The lattice thermal conductivity is greatly reduced by this boundary scattering. But when you think about keeping these nanowires isolated so that they are indeed one-dimensional conductors, and then packing them as closely as you can, it becomes more challenging to realize any significant benefits from this approach. So trade-offs everywhere you look, but if it wasn't difficult, it wouldn't be fun. Now, let's take a look at ballistic versus diffusive transport. If I think about ballistic transport, electrons just enter from a contact and shoot across like cannonballs and go out to second contact. We have been discussing long traditional thermoelectrics that are many mean-free paths long, and electrons undergo a random walk from one contact to another. So in the ballistic case, the transmission is 1. In the diffusive case, the transmission is much less than 1. So what we'd like to look at is, how do these thermoelectric transport coefficients change if we have ballistic transport? So the easiest way to look at this is not the conductivity, but the conductance itself. So if I look at the conductance, it's 2q squared over h. times the number of channels in the Fermi window, and the transmission in the diffusive case is average mean free path divided by L. Now, in general, the transmission is mean free path divided by mean free path plus L. If I go to the ballistic limit, the transmission goes to 1 because L is much less than the mean free path. So I simply replace this factor by 1. If I multiply by area, divide by area, I'll make it look like my bulk expression. Then I can convert it to a conductivity in the ballistic case by writing this conductance as ballistic conductivity times area divided by length. See, I've already got an area here, so I have to divide by length and then multiply by length. And the result is that this will be our expression for the conductivity when the transport is ballistic. And you'll notice that something very interesting has happened. We simply take our traditional expression and we replace the average mean free path by the length of the conductor. The simple physical explanation is that there's a lot of scattering in the first contact. Electrons go ballistically across the structure with length L, and then they immediately scatter in the second contact. So the average distance between scattering events is just the length of that ballistic channel. So it turns out to be very easy to take our transport coefficients and rewrite them in terms of ballistic conditions. We simply replace the mean free path by the length of the conductor. And if we want to be more careful, we simply replace it by the appropriate transmission. Now, there is a class of devices for which these effects can become very important. These are thermionic devices. And the thermionic devices have been explored by Professor Shakuri a number of years ago. It's a very interesting concept that looks a bit different from the thermoelectric devices that we've talked about. So we have a contact region that's heavily doped N-type. We have a barrier in the middle, and then we have another contact region. We apply a bias across this structure, lower the potential, and then we rely on thermionic emission over the barrier. That thermionic emission requires that the electrons absorb heat to hop over the barrier, so there'll be Peltier cooling that goes on. So it's a cooling device. If we apply a small voltage, we've been using small voltages for thermoelectrics, we could ask, what is the electrical conductivity, Seebeck coefficient, and Peltier coefficient, and electronic thermal conductivity for this structure, and how does it compare to the traditional thermoelectric structure? Okay. So before we launch into the analysis here, let me just explain the physics of what's going on here. In the N+ region to the left of this energy barrier, we have a thermal equilibrium Fermi-Dirac distribution of electrons. The probability that states are occupied is close to 1, well below the Fermi level, and very small, well above the Fermi level. Electrons that have a longitudinal energy that is above the barrier height can flow from contact 1 to contact 2. And when they do that, electrons are depleted from that high energy tail of the distribution. Okay. Now, in order to maintain that thermal equilibrium distribution, the electrons have to absorb thermal energy from the lattice, and those electrons will gain energy and fill in that thermal equilibrium distribution again. So that process then results in heat being absorbed on the left of the contact. That's Peltier cooling, and then heat being dissipated to the right of the contact. That's Peltier heating. Okay. All right, so detailed simulations by Professor Shakuri's group shows that that's exactly what happens. These are numerical simulations of the process. This is the amount of heat dissipated from the electrons to the lattice. You can see it's negative on this side of the barrier, meaning that the electrons are actually not dissipating heat. They're absorbing heat and cooling. There are some transient effects that occur in this small barrier, and then you'll see the electrons dissipating their heat to the lattice, the Peltier heating on the right side of the barrier. So the heating actually occurs before the barrier, or the cooling appears before the barrier, the heating appears after the barrier. Okay, so we could go through now and we could calculate the 4 thermoelectric transport coefficients for this different device. Let me just do the Peltier coefficient, and then I'll quote the results for the others. So let's start with our expression for the electrical current, this Landauer expression. We're going to try to calculate the heat current pumped by this device. So instead of charge flowing, we have heat flowing, and we have to put E minus EF inside the integral and then integrate over all of the channels. We'll assume a small voltage applied across this device, so we'll do the same Taylor series expansion we've done in the past. And then we'll get an expression for the heat flux from this. And we'll find that the heat flux pumped is proportional to the small voltage that's applied. And we'll get expressions that look sort of familiar from our thermoelectric expressions. Now, we need the transmission. Well, if the barrier is thick enough, the transmission is 0 for energies below the top of the barrier, if electrons can't tunnel through the barrier. And then once they get over the barrier, there might be some scattering that could return it to the left contact. The transmission would just be mean free path over mean free path plus the thickness of the barrier, if it's above the barrier. Okay. So we put that expression in. We begin integrating from the top of the barrier above, because that's the only place where we have any transmission. We'll get this complicated looking expression. Now, if I divide QV by electrical current and multiply by electrical current, then I can write this heat pump as some set of complicated looking constants times the electrical current. Those constants look like a Peltier coefficient. And what we'll find is that V divided by I, that's just resistance, or I divided by V is just conductance. So we'll get conductance downstairs. So we have heat pumped is Peltier coefficient times electrical current. We can do that in a current density per unit cross-sectional area. We'll get an expression for this Peltier coefficient. And we'll find that our Peltier coefficient looks very, very similar to what we've seen before. In fact, this expression is exactly what we had for traditional thermoelectrics. The differential conductivity is almost what we had for traditional thermoelectrics. It's just that the mean free path is replaced by something I'm calling an apparent mean free path. And what is that apparent mean free path? Well, it turns out to be just the smaller of either the actual mean free path or the thickness of the sample. So what's happened here is that the bottom of the conduction band has been replaced by the top of the barrier, because only electrons that go above the top of the barrier can carry any heat or charge. The mean free path has been replaced by an apparent mean free path. For very thick barriers, then this apparent mean free path just becomes the actual mean free path, and we have exactly the same result we had for traditional thermoelectrics. For very thin mean free paths, this apparent mean free, for very thin barriers, small thickness D, the apparent mean free path becomes the thickness of the sample D. That's just what we saw in ballistic transport. So in that case, the expressions just go to the expressions we had earlier for ballistic transport. So what we find in these thermionic devices is that when we calculate the transport coefficients, it looks very similar to a thermoelectric device. They're very similar to bulk materials, and that sort of asks us to think, now, why are they so similar? Well, in the thermionic device, what we have is energy filtering going on the left side of the barrier. Only electrons with an energy above the bottom of the barrier height can go over. Only the high energy electrons that can carry their heat can transmit. This barrier filters out the low energy carriers. And then we have Peltier heating when that excess energy is dumped on the other side. So energy filtering occurs at the barrier in the thermionic device. Now, what happens in the thermoelectric device, which in the end mathematically looks very similar? In the thermoelectric device, electrons have to hop from the Fermi level in the metal up into a state in the conduction band. So we filter out the electrons that don't have enough energy to hop up there. The Peltier cooling occurs because of that energy filtering process at the contacts. The electrons flow across in the channel, and then they dump their excess energy in the second contact. That's Peltier heating. So in this traditional device, the energy filtering occurs at the contacts. Now, that would lead you to believe that there's no difference between these two devices. There's no reason to prefer one versus the other in particular. Now, it turns out that there are some second-order effects. Once you start stacking devices together, there are considerations about how long it takes for some transients to relax, and spacings of energy relaxation lengths become important. And one can look, and under certain conditions, one can find some benefits if one carefully designs a set of thermionic barriers in series. There are also interesting effects that Professor Shakiri has thought about momentum conservation at this interface. But I think the message is, again, that to first order, the devices are very similar. We have to look at more subtle issues to see whether we can find some performance advantage in one versus the other. We're still looking for the killer solution that will give us large increases in the power factor. So, just to wrap up, these are the topics that we discussed. I just introduced you to the fact that realistic band structures can be much more complicated. We'll talk about that in the lecture by Dr. Mason at the last lecture in week 2. We discussed the fact that it's really difficult to identify a single optimum band structure. The general trade-offs can be appreciated, but we're still trying to understand, is there a band structure that will give us distinctly better performance? We've seen that the way to think about reduced dimensionality thermoelectrics is mainly as a way to engineer the number of channels in energy space. We've learned how to think about ballistic and diffusive transport, and we've seen that thermionic devices are in many ways very similar to thermoelectric devices. Okay, so those are the basic conclusions. Now, just as kind of a transition to the next lecture, I'll remind you that what has proven most effective over the last decade in improving the performance of thermoelectric devices has been working not on the electrical part, which we've been discussing here, but on the lattice thermal conductivity. And that's the subject of the next lecture.